Good evening, class. Welcome to video 2 of topic 1 of unit 4 electric fields. This video is going to be covering the main ideas of chapter 6.2 of book 2. Please complete this reading before next class. So here are your learning intentions and success criteria for this topic. Please pause the video and attempt to complete the KS table on your own. Alright, hopefully you've got that finished now. So, our learning intention, we're going to understand the concept of electric fields, and I want you to be able to predict field effects on charged particles. So, we're going to need to, in terms to succeed here, you're going to need to construct some electric field diagrams, you're going to need to interpret them, and then you're going to need to be able to calculate them using the two equations. So the first is, well, firstly, what is an electric field and how do you draw it? So there's kind of a knowledge and a skill there because you've got to know how to do this thing, and you've got to know what these field equations are. How do we calculate those fields? So let's start with the idea of fields. Imagine that you measure something about the room that you're in right now. It might be the temperature, it might be the amount of light that you're getting in the room, it could be humidity, air pressure, noise level, whatever you measure, you've got a single point of data. Now go to every room in your house and measure that same thing in every room in your house. This data set would be called a field. Okay. Now, you've seen fields in a few different places. At night, if you watch the news, you would see temperature and air pressure fields on the news. So here's a temperature map from yesterday for Australia, and you can see here that we have data for all over Australia, and they've colour-coded it there to help us visualise it a bit and understand it a bit easier, but this is a field. Here is a weather map, so in this case a bit more granulated, so it's only got certain places, but this is still a field. Here's a pressure map, so for air pressure. Again, we can see air lines here that are saying that they're the same pressure, so there's a 1028, there's a 1020, a 1012, but again, in this case, instead of drawing every single point, they've just connected the points that are the same. That'll be useful in our next chapter, the idea of when we talk about equipotentials. Let's see what else we've got here. Here's one from the Year 9 Geology unit in looking at the age of the crust as we move away from plate boundaries. Again, this is a field. Okay, these are all called scalar fields. They measure only one thing. They measure just a value. If you think about it, the Cartesian planes that you've been using for graphing since grade 7 or grade 8, those are position fields because, again, they measure some number, some sort of information, and we could look all over it and get that same information. Now, here's a different type of field. This is a wind field. We've still got the pressure isobars on there, but here we can see the wind direction, and we can also see the wind strength, and so they're using arrows instead of just numbers. Now, arrows are quite useful here because they show the direction and they show the relative size quite easily. Like, I don't know what the numbers are, but I can tell that over here the wind was a lot stronger than it was over here in northwest southern Australia there. There's some really tiny ones over here through the middle of WA. So this was today, actually, at 4 o'clock this afternoon, and I can say, well, over here not much wind, but over here off the coast of Queensland, we've got lots of wind over there. So I don't know what the velocity is, but we can look at the chart and go, and it tells us some information. We can look at the field and it tells us some information. So this is a vector field. It shows both magnitude and direction. Okay, now in our first video and the simulation we did in class, we saw that as you bring a charge closer to another charge, the force between them increases. Remember, while whether something is positive or negative will tell us what direction it goes in, it didn't matter in that as we brought them closer, the field always got bigger. Just the direction might have been flipped if you had a positive and a negative, or two positives or two negatives. So I've gone back to that simulation. I've taken a range of measurements and I've plotted them at 1 centimetre increments. So here we have when a charge is here 10 centimeters away from another charge. Now, you can't see the other charge because the arrows got so big here that they started to get very unwieldy to graph out and see clearly what was going on. But we can see here as we go 10, 9, 8, 7, as we move through this direction, we see the vector arrow getting larger and larger. The force is getting larger. I didn't put the numbers on there, but we can still see the relative thing increases. And this is what we call an electric field. In this case, I've only got one dimension, just a straight line, but we could go and look at that simulation we saw today and see the field in a 2D space. Any electrically charged object has a field around it that influences other electrically charged objects, and that's what we call the electric field. Okay? The electric field is about showing the force that a test charge of +1 coulomb would experience at that point. Now, here is the very formal definition of what a field is from QCAA, and I did want to look at this very briefly because it'll help with your understanding of magnetic fields when we get to it, and gravitational fields, which is on the other year, so last year for the current year 12s and next year for the current year 11s. So a field is a position in space where susceptible objects experience a force or acquire potential energy as they are worked into that position. Okay? So if we think about an electric field, if you've got two positives, you have to work it, you have to apply some energy to bring it closer to that positive charge. If we have a gravitational field, you've got to do some work to lift things away from larger gravitational objects. You've got to put some energy in to lift something off the ground. Okay, so it's a position. In this case, we're generally going to see 2D positions because we can't really easily draw 3D stuff onto pieces of paper for exam. We're susceptible objects, so it has to be susceptible to it. So if we're talking about an electric field, it has to be something that responds to electric charge. Something that is neutral, for example, would not respond to an electric field. However, if we had just a single charged electron or proton, or even a bunch of electrons and protons, as long as there is some net charge on the object, we would have some sort of field acting on it. Right? And a force, a push or a pull, or it can acquire a potential energy as we do some work to it, and that will matter for our next topic 6.3 when we look at equipotential and work. So electric field, and this definition goes on a little bit longer with different types of fields, but here's the definition for an electric field. A region of space, okay, so we're talking about the whole area versus just a single position, but a region of space near an electrically charged object that exerts forces on other electrically charged objects, and that's that susceptible object. Okay. Now, the thing about this is that reminder, electric fields by convention are about how it affects a positive charge. A negative charge will feel the same field in the opposite direction. So all the stuff we see in terms of drawing, in terms of the math that we're going to do, is always about positive charges. And then after you do that, if you're dealing with a negative, you're going to have to flip it. There's no nice easy way to just go, oh yeah, that's positive, that's negative. In the math, you have to sort of just read your questions. Alright, so let's have a look at drawing electric fields. So here are 4 drawings from the example, from the textbook. Up the top here we just have a single charge on its own. It's a negative charge there. The arrows are a little bit small. I do apologise, I needed a bit of space for text, but please open up your textbook and have a look at this diagram. It is on page... let's find it. It is on page 163. So here we have a single charge. We can see that the field lines are radiating outwards. In this case, because it's negative, the field lines are coming into it. Here we have a positive and a negative charge. We can see the field lines are running from the positive to the negative. So over away from it, it looks very much the same as the single charge. But when they're together, they start to interact and the fields change. Here we have 2 positives and a negative. So we can see the positives flowing to the negative, but the 2 positives are curving away from each other. They don't want to give anything to each other. And here we have, this is an interesting one, these are 2 capacitive plates. sort of if you think about it like a battery effect or cells in a battery, and you can see here that the field lines are very straight between them with a bit of bending at the end, and that will be significant. So there are several points here, 5 main points actually that we can take from this, 4 actually real ones and then just one as a sort of just as a reminder. Our first is that the lines never cross, and if you look at all these pictures here, even though the resolution is a little bit low, you can see that none of the lines cross. Okay. Second convention, they go from the positive to the negative. So here, down here we have some positives, and we see the arrows on C here are going away from the positive charge into the negative charge, and the same thing here and here. Here on this solo one, the arrows are pointing into the negative. So again, take a look at that picture in your textbook. Field lines must enter or leave the surface perpendicular to the surface, which is why here you can see that they're at right angles to these flat surfaces. But here on the curved charges or the curved objects, and we generally think of protons and electrons as being just sort of round balls in this sense, they are leaving perpendicular surfaces. And this is the most important one, I feel. I'll cut off my picture a bit there. In a given area, the number of lines represents the field strength. Okay, because if we have a look at here 4, if I draw a box, and it doesn't matter what box I draw inside between those two plates, I will get the same amount of lines in any per given area. Okay, and because I get the same amount of lines per given area, that means that the force will be the same, because the field is the same. If the field is the same, the force is the same. We'll get to that in a second. While here, if I drew a circle up at here, far away from the charge versus very close to the charge, the field is not going to be the same. Same thing with here. I could draw, you can see here, if I draw a circle that given the size here, there's a lot more lines going through it than the same circle off to the other side, the left side of the positive charge. Okay, so this is a really important one, and this last one's kind of a reminder. While we're only drawing in 2D, they do exist in 3 dimensions. So there would be, some charge coming up, out, and then back down to it, and some going in and back up towards the negative charge. So while these are just 2D pictures of 3D things. So let's talk about electric field strength. Because field strength is defined as how hard the field pushes, okay, our force, per charge being pushed, we've got a nice simple equation here. So here we have E for electric field strength, Fe, so our electric force. Remember, in the syllabus it just writes F, but F for electric force felt at that location, and Q is the charge at that location. Okay? That's going to be really important because we're going to see another formula in a second that uses a different type of Q. So this one here is for when you have a force and you have a charge somewhere in a field that you know the strength of, or you might know the force and you know the charge, but you've got to work out the field. Okay, so this is when we're using, you can think of little q here as the test charge, the thing that gets moved around some other type of charge. Okay, now we're going to have to do something a little bit different because, as I've said, my pen has decided to go kaput. So we're going to do a couple of worked examples, but we're going to do them on paper. So here's our first worked example. A short length of nichrome wire is held vertically under an overhead power wire where the field strength is blah. Calculate the force experienced by an electron, and they've reminded us here that the charge on an electron is negative 1.6 times 10 to the negative 19 coulombs. Now, I've mentioned this in class. That is a number you'll be expected to know how to find on your exam. Either memorize the number, not that hard a number, but it is provided to you as the fundamental charge in your formula booklet. So this is a number that often they might just say, yeah, what's the force experienced by an electron? And that's where they would end. Okay, they wouldn't remind you that this is the electron charge. You'd be expected to go, oh, it's an electron, it's fundamental, go find it out of my formula booklet. There it is, off we go. Alright, so be aware of that. Just move this out of the way. And I will turn on my light. Apologies for that as the correction kicks in. Okay. So as we have a read through the question, and I really recommend having the textbook up as I do this, because obviously I can't have the tablet up at the same time, so I've got some paper here. We can see a couple of numbers. We've got 5,000 newtons per coulomb. That's our field. So let's write that. This is 6.2a. So we have our field E equals 5,000 newtons per coulomb. Now, often, remember, electric field is a vector. We should put an arrow above it, but a lot of times people just get a bit lazy and sort of forget about it. So don't stress about it too much, but try to remember. And we're told that our Q here equals negative 1.6 times 10 to the negative 19 coulomb. Okay, and we're after our force. Force equals unknown. We only have one equation for electric field at this point, so it's a nice easy one. E equals F over Q. I'm going to rearrange it first today. Let's be different. F equals E times Q equals 5,000 times. Now, the way that Walding likes to do it is he doesn't put negatives in. I'm going to put the negative in for a second, because that will help us understand what our answer actually means. Negative 19 equals negative 8 times 10 to the negative 16 newtons. Okay, so we're going to use the same, we already saw forces, and we talked about negatives and positives before. Let's think about this. We have a power wire, we have some sort of wire here, and it has a field coming out of it. Just drawing as a straight line, as a uniform field, and we have some charge here. Here's our little electron. So if the field is acting downwards, because it actually says here that the field strength is blah 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 downwards, so I might actually put that here. Then that tells us that our electron must do the opposite, because remember, electric field is about what would happen to a positive charge. If we have an electron is a negative charge. And so that must mean that our force is that it is 8 times 10 to the negative 16 newtons upwards. Okay, so our electron has some sort of charge upwards. And that looks okay on my screen, so hopefully the resolution's alright when this goes up. Alright, so that one was a fairly straightforward one. Now, the next worked example has a little bit of complexity on it, which we actually can skip. Let me just bring the back over. Good. Now, this is our second worked example. We have a proton, we've got our charge there, and a mass is introduced. Now, both of these numbers, by the way, again, you'd be expected to realise that you could look them up in a textbook. In the formula booklet. The mass is provided to you in the constants, and you're expected to remember that the charge on a proton is exactly opposite the charge on an electron, and as I've already established, the charge on an electron is present in your formula booklet. Introduced at rest into an electric field that has a constant field strength of 4 times 10 to the 3 newtons per coulombs. Now, what's kind of good for you guys, and I am taking a kind of stab in the dark on this, because this first one, part A here, that is all about electric fields and electromagnetism, which is part of your current. So if you're watching this in a year where I'm teaching this to you in class right now, this would be part of your final exam. But these other three things here, the acceleration, the time, and the distance, that's linear motion. And linear motion is not part of Unit 3 and 4 for electromagnetism, for the alternate sequence of physics. It is part of the main sequence, or could be considered as part of the main sequence. I believe linear motion is Unit 2 for them. So this might not even appear on an exam for main sequence schools. So I am going to do BCD quickly, but if you're uncertain of it, I can guarantee for year 11 I would not put this sort of question on the final exam, and for year 12 this is really outside the scope of Unit 3 and 4, because Unit 3 and 4, Unit 3 is all about heat, circuits and waves, and Unit 4 is about electromagnetism and quantum mechanics. There's no linear motion mentioned anywhere in those descriptors. So I'm going to do A. I will briefly run over B, C and D, but I will not explain B, C and D. You can have a look at what they've written in the text. Alright, let's load up a bit of light. Alright, so example 6.2b. Question. So again, we have our charge, Q equals positive 1.6 this time, times 10 to the negative 19 coulombs. And we have a field strength here, E equals 4 times 10 to the 3 newtons per coulomb. Alright, and so now we can use the same formula as before to work out the force on it, because that's what part A is after. So for part A, we are after the force. So again, same formula, E equals F over Q. F equals E times Q equals 4 times 10 to the 3 times 1.6 times 10 to the negative 19 equals 6.4 times 10 to the negative 16 newtons. Now it is a positive number and we're using a positive charge, so it'll be the direction of the field. Now they've given us a picture of the field in this case, so I'll just quickly sketch that out. We have a region here that is positive, we have a region here that is negative, so our field must be going, remember, from positive to negative. And so this force must be acting in this direction because it is a positive charge. Positive charges go from positive to negative. If you think about it, well, positives don't like positives. It's going to get pushed away from it, which is why it would go this direction. So I'm going to put here my direction to the right. Now, the rest of the question is linear motion. Part 2, or Part B, they're asked for the acceleration. We're given the mass of the proton. Mass equals 1.67 times 10 to the negative 27 kilograms. And we've just worked out the force, and we need acceleration. Oops. A equals unknown. That's Newton's second law. A equals F over M equals 6.4 times 10 to the negative 16 over 1.67 times 10 to the negative 27. Will give us an answer of 3.83 times 10 to the 11 meters per second squared. C asks us, well, what is the time to reach a speed of something? The question does say it is introduced at rest, so we know that our initial velocity must be 0. We want to try to get to a final velocity of 2 times 10 to the 5. I do just want you to notice for a second, this force is exceptionally small. I mean, 10 to the negative 16, that's very, very tiny. But the mass is so small that our resultant acceleration is massive. Okay, so 10 to the power of 11, that's like that sort of acceleration being applied to us would probably squish us into paste, because we need a lot of force to do that. We know our acceleration, and we are trying to find a time, and we know an A, so that would be V equals U plus AT is going to be our formula, plus AT. 2 times 10 to the 5 equals 3.83 times 10 to the 11 times t, and if we rearrange that, we'd solve that t equals 5.22 times 10 to the negative 7. So 2 times 10 to the power of 5, I mean, that's pretty fast, 20,000 meters per second. But still, because of this massive acceleration, the time does not take all that long. And the last it wants is the distance. Let's see, we have a time, we have a U. We could use several different formulas. I will just use my S formula. S equals ut plus a half at squared. U is 0, so that'll just cancel. S will equal a half times A, which is 3.83 times 10 to the 11 times 5.22 times 10 to the negative 17, and that is squared. So S would just equal 0.0522 meters, carrying through our 3 sig figs. So these part B, C, D, again, that is more for next year's stuff. However, just so that you've got it there to see how we'd work it through. But you know, even though if you're in year 11 this year, you would be able to follow this through, because that formula, you did see that in year 10. Alright, so those are how we would find electric fields, or how we would deal with electric fields if we have some sort of probing, what's what I'm looking for? Some sort of probing charge that is being placed into a field. Okay, but there is another way to work out electric field strength. Okay, and this formula instead looks at the source charge, what's creating the field. On the previous one, we were just told there was a field. It might be uniform, might not be uniform, we don't know. We're just told here's a number for the field, and here's the work out the force. Or we could be told here's the force, work out the field. Or we could be told here's a field and here's the force a charge feels. How big's this charge? But it doesn't tell us what the source charge is. Okay? And so the formula that we use to work out source charge looks like this. Now, the textbook takes the 1 over 4 pi epsilon naught and just replaces it with a K, K for Coulomb's constant, even though Coulomb does not start with a K and neither does constant. It's just a long-running joke in physics that all constants seem to be given the letter K. And the way it's provided in the formula booklet looks like this. But the full way it's actually written, they write it like this, that E equals F over Q. That's our first equation that we just worked with, which equals this thing here. Okay, so reminder, the 1 over 4 pi epsilon naught here, that is given to you in your constant section to say that that bit there equals 9 times 10 to the power of 9. And then you have a Q and R over here. So the Q in this case is our source charge, and R is the distance from the source in meters. Okay, so it's still the same radius that we had before. I think this is why the syllabus has given you the electric force equation with 2 different types of Q's, so that when you get to field strength, you can go, well, little q is my test charge, my one that's out somewhere in a field, but big Q is my source charge, the thing that is creating the field that we're probing in. That to me is the only reason I can see that they've done this. There might be other reasons, but that makes sense to me. So we'll just try to run with that idea. So let's have a look at a couple of examples on this. So here's C. Calculate the electric field strength. 1 nanometer, they've given us a distance, from a proton. Okay, so because they've told us a distance, we know we need to use this second formula. And we'll just move this out of the way. And we will turn on some light. Alright, so 6.2c. We are told a distance, the radius, so the radius is going to equal 1 times 10 to the negative 9 meters. Now, converting nanometers into meters, you're expected to be able to do. The list of metric conversions is part of your formula booklet, so you should go to look that up if you need to. I'll just do that as 2 steps for a second. So I'll leave that as meters. Radius equals 1 nanometer. So you see the word nano, you replace it with that times 10 to the negative 9. We have our source charge is a proton, so positive 1.6 times 10 to the negative 19 coulombs. And we are after the electric field strength at that distance. E equals unknown. And feed it into the equation. Now, the way that Walding does his worked example for this is he's using K over R squared, alright, which shouldn't be an issue, but as a just in case, I would maybe write 1 over 4 pi epsilon naught Q over R squared. It may just be easy to be a bit pedantic about it and write this long stupid thing. They mean the same thing, but it is what it is. 9 times 10 to the power of 9. Q is equal to 1.6 times 10 to the negative 19. And our radius is 1 times 10 to the negative 9 squared. Do not forget the whole thing must be squared. I know there's a 1 in this case, but sometimes people do just the squaring of the power and forget the number at the front. It won't matter in this case because 1 squared is 1, but if you had 3 times 10 to the negative 9, well, you then end up with 9 times 10 to the power of negative 18, not 3 times 10 to the power of negative 18. You must make sure that you're using your calculator properly. So, speaking of calculators, we plug that in and we will get 1.4 times 10 to the power of 9 Newton coulombs. Now, it's an electric field, it's a positive charge. Okay, so it's positive. This is important. And so if we were to draw this, we could say, well, here's our positive, here is our field going away from it, and if this distance here is 1 nanometer, then at that point E equals 1.4 times 10 to the 10 to the positive 9. But notice my arrow is drawn going away from the charge, so I need to write that there. Do not forget your directions. Okay? I guarantee you they will pick that if you forget your directions. So that was a fairly straightforward example. Our last example is 6.2d. This is a bit more complicated. Figure 10 shows two point charges. Point charges just means we don't need to care about how big the charge is. I'm pretty much certain that anything you see during year 11 and 12 will be a point charge. Okay? I mean, definitely year 11, I'm not going to make you do other charges, but year 12, I can't see anything here that suggests you need to be able to do actual 2D or 3D shapes with charge. Everything will just be a point. We're told here it's separated by distance, and we want to find what is the field strength directly in the middle. Now, field strengths are vectors, which means to work out the total vector at a point, we just need to know all the vectors affecting it and add it up together. So we're going to work out two fields and add them together. But part B is the interesting one here. We want to find the point where the field strength is 0. Because one is equal to 3.5 micro and the other is 2.5 micro, that tells us that there is going to be some distance where somewhere probably over here, because this is a little bit stronger, somewhere over on this side that says that's where the two things should cancel, because they're both pushing there. If one was a push and the other one was a negative, the cancellation point would have to be on the opposite side of the negative. But because they're both positive, it has to be somewhere in the middle between the two. So, this time I'm going to redraw the picture first. We have Q1 equals, actually I will use capital Q so we can stick with the convention. Q1 equals 3.5 microcoulombs, and we have Q2 equals 2.5 microcoulombs. We have the distance between them is 15 centimeters. Actually, I'm going to put R because it's not an distance equals 0.15 meters. And we are after this point X, which is right in the middle. So let's call, we've called them 1 and 2, so let's work out the electric field for number 1 at this point in the middle. So the electric field for 1 will have R equal to 0.075, 7.5 centimeters is half of 15 centimeters, and we have that Q equals, or Q1 equals 3.5. We have micro, so turn it into times 10 to the negative 6 coulombs. And we plug that into our formula. I'm just going to use K notation because writing out the full epsilon thing sucks, over R squared. We substitute those things in, 9 times 10 to the 9 times 3.5 times 10 to the negative 6 divided by 0.075 squared will give us an answer of 5.59 times 10 to the 6 Newton coulombs, Newton per coulomb, sorry, to the right. Okay, because the Q1 field, that's positive, will be going out like this, and the Q2 field, because it's positive, will be going out like this. Right? Let's have a look at, this was E1. Let's do E2. Now radius is the same, because we're halfway. Q will be different, because it's 2.5 times 10 to the negative 6. I'm just going to substitute in the formula, so we would have 9 times equals E2. 9 times 10 to the 9 times 2.5 times 10 to the negative 6 divided by 0.075 squared. E2 would equal 4 times 10 to the 6 newtons per coulomb, newtons per coulomb left. Okay, so if we think about this, some point here in the middle, we have a 5.59 times 10 to the 6, and a, I'll do this in a different colour, and a 4 times 10 to the 6 in the opposite direction. Well, if we add these together, again we add them head to tail, so we're going to have 5.59 and then 4.6, and so what we're trying to find is this length here. Because 1 is going to the left, let's say the 1 to the left is negative. So 5.59 times 10 to the 6 plus negative 4 times 10 to the 6. Remember, we can use negatives to represent opposite directions. And we would end up with the total electric field, I'll go ET, E total, equals 1.59 times 10 to the power of 6 newtons per coulomb. Okay, and it's positive, which means it must be rightward, so I'm just going to draw an arrow to say it's that way. Okay, so that one, I mean, it was longer, but it is basically the same thing. It's just do it a couple of times and then add the pieces up. And in all those simulations we've seen in class, they're just doing this with every single charge that you put on there at every single point, and then working out what the final result is. It's not hard math, it's just lots of the same math, which is why computers are really good at it. Okay, now let's have a look at the second part. We want to know where on this length of distance equals 15 between charge 1 and charge 2 does E equals 0. And we know at this point here in the middle it equals 1.59 to the right, so there's still a little bit there. So it's going to be somewhere over here that there's going to point here where E equals 0. As we just saw, if we wanted to make E equals 0, well, these two numbers would have to have the same size. We would have to have the E E1, magnitude of E1 equals magnitude of E2, or E1 plus E2 must equal 0. Okay, so that's what we've got to basically figure out. Now, the trick for these sort of questions, and these sort of questions pop up a lot. Okay, question writers love these sort of questions. If we were to I'll put this out as a formula. So we need where E1 plus E2 equals 0, or we need where E1 equals negative E2. Now, Walding does some stuff with, that's what I'm looking for, absolute magnitudes instead, which can also work. We'll see whether my answer gives me the right answer, or if we need to go do a magnitude. I mean, this expression is perfectly fine, so we'll just see what happens. Let's substitute in our formulas for our e's. We know that E1 equals K Q1 over radius 1 squared, where radius 1 is the distance to this point. Let's draw it so that we've got kind of a way of visualizing it. So this distance here would be radius 1. This distance here would be radius 2. We've got Q1 and Q2. Let me just double check. Yep, good. And that's going to equal negative K Q2 over radius 2 squared. Now the good news is we can see that there's K on both sides. They're going to cancel. That's fantastic. So now we have just Q1 over radius 1 squared equals negative Q2 over radius 2 squared. Alright, well, we've got Q1 and we've got Q2, that's good, but we don't know R1 and we don't know R2, that's bad. We have two unknowns but only one formula. But the really good news is we know that this whole thing is 15. So one way of writing this is that R1 plus R2 must equal, not 15, sorry, 0.15, 0.15. Okay, we could use 15 and get centimetres out of this, but I'm going to avoid it. I prefer to use SI units. So let's turn R2 into R2 equals 0.15 take R1. And now we can substitute this in, and we get that Q1 over R1 squared equals negative Q2 over 0.15 minus R1 squared. Okay. It will be a sort of nasty looking quadratic, but there's the potential to be a nasty looking quadratic, but we'll see if we can skip that. So, let's rearrange this. We're going to get Q1 and Q2 are just numbers, so we'll just leave them alone for the moment. Q1, we'll make the negative over here now, over Q2 equals R1 squared over 0.15 minus R1 squared. Now you didn't have to do it like this. You could have expanded this open, put the numbers in, multiplied things over, and you would have got some quadratic at the end, but there's this nice little solution here where, because you've got both an R squared over something squared, the squareds you can just take the square root of both sides. Okay, let's start putting in numbers. For Q1 and Q2 we have 3.5 times 10 to the negative 6 over 2.5 times 10 to the negative 6, and because it's both got times 10 to the negative 6, that will cancel. Equals R1 squared over 0.15 take R1 squared. Okay, let's take the square roots of both sides. So we're going to have the square root 3.5 over 2.5. Should be square rooted equals R1 over 0.15 take R1. Square root, let's see, 3.5 over 2.5 is 7 over 5. Square root of that, 1.183 equals R1 over 0.15 take R1. Multiply that over, we get 1.183 times 0.15. Oops, sorry, that should be... that's why that they've done it like this. So I've just completely forgot about my negative all of a sudden here. I'm actually going to get rid of that negative. Can't leave the negative there. So the reason that Walding's done it like this is to avoid dealing with that negative sign. And this one method does work. However, there is a slight problem in that it does skip a solution, or does skip a possible solution. So we're actually going to have to go back and I'm going to get to here. I'm not going to do this square root thing. I will do this same step here though. I'm going to have negative 3.5 over 2.5. The cancelling of the 10 to the power of 6's will still work. Equals R1 squared over 0. Well, I'm going to expand this open. Let's grab out the calculator. So 0.15 to the power 0.15 to the power of 2 equals 0.0225. Let's see. We're going to have a plus R squared, and then we're going to have minus 0.3 R on our bottom there. And so this is going to be negative 1.4 on that side, and that's going to be negative. That's going to just go to negative 1.4. Okay, now let's rearrange. I'm going to multiply all this bit at the bottom over the other side, and I'm going to do the calculation as I do it. So 4 times 0.0225. So I'm going to have a negative 0.0315 minus 1.4 R1 squared plus, because a negative times a negative will be a positive, 1.4 times 0.3, 0.42 R1 equals R1 squared. And then we can subtract this R1 squared to the other side. So I'm just going to get rid of that and say that is now 0, and this will be negative 2.4 R1 squared. And we have just a quadratic. It's not a pleasant looking quadratic by any means, but it is just a quadratic. Now, you are expected to be able to use the quadratic equation. What I'm going to do is shortcut myself, and I'm going to go over to Wolfram Alpha, and I'm going to type this quadratic in. Negative 0.0315 minus 2.4 squared plus 0.42x equals 0. I know it's r, but I just deal with x's in my head. And we get that our it's interesting, it's giving us a complex solution here. So I think it's kind of a weirdly worked question, but if we look at the solution, it gives us that one of the roots has the real part of the root is 0.0875. And the other one, yeah, the real part is always that, and then there's a complex part of it. Equals R1. So let's see if that makes sense. If that is saying here that R1 is equal to 8.75 centimeters. Okay, well, let's have a look at the roots. They've got 8.13. So it looks like something here in this process has not worked well for the way of doing it. Now, Walding does use just taking the magnitude of both as being the answer, as being the solution, and then going from there. which isn't a terribly difficult thing. So let's have a look at that very briefly. He uses the idea that the electric field for 1, electric field for 2, and just taking the positives. So that way it doesn't have that nasty negative sign. So I'm going to skip forward a couple of steps. And so that way he ends up at this point here, 3.5 over 2.5, because there's our q's with the 10 to the power of 6 cancelled, over, what has he got here? S, or he's used S, but we're going to use radius 1 squared over, he's gone with 15 as the thing. I'm still going to use 0.15. Take radius 1 squared, because remember we got that from showing that radius 1 plus radius 2 equaled 0.15. And then he takes the square root of this, and this square root cancels off those and puts a square root there to get that 1.183 equals radius 1 over 0.15 take radius 1. Rearrange that and you get that, where's my calculator? 1.183 1.15. Yeah, that's why I didn't have that 1.83. Just had to double check something. So that's 0.17745. Take away 1.183 R1 equals R1. Let's add that to the side. 0.17745 equals 2.183 R1. And then if we divide that over, we would get, divide by 2.183, you get that R1 equals 0.0813 meters or 8.13 centimeters. I'm curious why that is so close to the other one, even though the answers are different, and I will go back and revisit it for a second to see if there's something else going on that I've forgotten. However, this idea of letting this core idea that I really want you to get from this work example, firstly, the idea the electric fields have to equal, but setting up this part here, that's the secret for a lot of these questions. You'll see it a lot in linear motion next year, year 11, so it's worthwhile sort of just wrapping your head around it, and it pops up a lot in math. This idea of setting up a simultaneous equation where you take something where you have two unknowns and write them in relation to something else that you know, so that you end up with just one unknown at the end with only R1s here instead of R1 and R2. Alright, so that brings us to the end of this lesson. So in this video we have learnt firstly, well, what a field is and how to draw it. I've typoed that there and said how to drag it, though, how to draw it, and how to calculate the electric field with a couple of different methods. So you should be able to do those things down there at the bottom, please. For your entrance slip to class, access chapter 6.2 in the Check Your Learning PDF, and then download those, do questions 1 to 5, and put them into the 4.1.2 space on eLearn. Thanks for listening, guys. Have a great evening. See you next time. Bye.